Welcome to today's Explainer. Look, we're watching a pretty fascinating shift in the AI landscape right now. As frontier models, especially ones like Kimi K3, get exponentially more powerful, we're all running into this critical realization. Raw power is just not the same thing as control. Actually, as these systems scale up, having a robust control architecture becomes exponentially more critical. And today, we're going to break down exactly why that is.
There's this quote from the research that I just absolutely love because it really hits the nail on the head. A system may become more capable of acting without becoming more capable of determining whether it should act. I mean, it is incredibly dangerous to confuse raw, brute computational horsepower with actual, governed intelligence. Just because an AI can generate thousands of lines of code or execute these massive, long-horizon tasks, well, that doesn't inherently mean it knows if its underlying assumptions are actually valid to begin with.
So here's our roadmap for this explainer. First, Kimi K3, power, not control. Second, architecture is not true coordination. Third, deconstructing AI benchmarks. Fourth, evaluating the energetic paradigm. And finally, metrics for true control. Let's jump right into part one. Kimi K3, power, not control.
This right here brilliantly illustrates the core distinction we have to make today. Think of it like the engine versus the steering wheel. Kimi 3 is an amazingly powerful execution substrate. With its 2.8 trillion parameters, it massively expands what an AI system can do computationally. But on the other side, we have the energetic paradigm, or EP. EP is a control architecture. It governs whether the system is actually solving the correct problem, respecting valid constraints, using reliable evidence, correcting errors, revising goals, and keeping things coherent over time. One gives you the power to move fast, the other makes sure you're actually heading toward a valid destination.
To really appreciate the engine of Kimi K3, we have to look past just the parameter count or benchmark rankings. Its deeper significance is how it integrates low-precision training, highly sparse mixture of experts routing, tool use, compiler construction, and long-horizon execution. Take its mini-Triton demonstration, for example. It didn't just spit out a text in a bit. It operated across a complete technical causal chain, optimizing and revising hardware code. It proves K3 is a highly capable substrate for autonomous engineering. But again, flawlessly executing compiler construction just isn't the same thing as broad, reliable engineering governance.
Which brings us to part two. Architecture is not true coordination. What's really interesting here is how the architecture separates memory from authority. Kimi K3 uses this thing called Kimi Delta Attention, or KDA, to efficiently carry information over very long contexts. It's a huge architectural win, for sure. But compressing and carrying history is not the same as EP's structured memory. A model might efficiently carry facts from the past, but it doesn't inherently know which of those assumptions have expired, which decisions are strictly irreversible, or which pieces of evidence have to stay inextricably linked to their source. Long context carries the past. EP evaluates if it's still valid right now. And we see a very similar distinction with routing. Kimi 3 has this highly sparse mixture of experts set up. That is amazing neural representation routing. But these MoE experts don't possess independent responsibility. A neural router is basically just selecting parameter blocks to process specific tokens. Intelligent coordination under EP is entirely different. That requires allocating reasoning, tools, agents, authority, and computational resources based on the actual structure and real-world consequences of the task at hand. So if an AI has a massive engine but completely lacks this institutional steering wheel, it begs a pretty provocative question. What do our current benchmarks actually measure? Are we testing the engine or are we testing the steering?
Let's look at part 3, deconstructing AI benchmarks.
When you step back and look at the whole evaluation landscape, there are basically 5 fundamental categories of benchmarks. Everything from static multiple-choice science questions to human preference voting arenas to repairing software repositories, right up to running 48-hour-long Horizon workflows. You literally cannot responsibly collapse all of these into one overall win rate. Answering a trivia question correctly, repairing a terminal repository, and winning a website preference vote are fundamentally different activities. They require totally different capabilities. The crucial takeaway here is this. Existing tests are great as compatibility and execution benchmarks. They evaluate the substrate's final output capability perfectly well, but they completely fail to measure the dynamic trajectory. They don't test for constraint preservation or error correction or if the model simply hallucinated its way to the correct final answer. If you're only looking at the finish line, you learn absolutely nothing about how the system was driven to get there. which means these tests simply cannot establish EP's distinctive value. Moving to part 4, evaluating the energetic paradigm. To properly test control, the source material proposes a really rigorous 2-layer evaluation strategy. Layer 1 is all about compatibility and execution. Here, we compare the exact same base model tested with and without EP. Notice how we hold literally everything else constant: the model version, the accessible tools, context window, token budget, time limit, retry allowance, all of it. We do this to prove beyond a doubt that EP actually improves task completion and reduces errors strictly through superior control, and not just because we secretly handed it a massive increase in computational resources. Once we've done that, we move to Layer 2, EP native evaluation. This evaluates all those capabilities that ordinary benchmarks rarely ever make visible. We're talking about problem formation, constraint discovery, causal reasoning, judgment, and institutional intelligence. Look, ordinary benchmarks don't test if an AI suddenly realizes halfway through a task that its original goal is completely invalid and needs to be abandoned. EP-native benchmarks are designed specifically to expose these higher-level cognitive control functions. Let's trace how this builds a complete trajectory. We have to observe the entire process, from the initial state to action, verification, correction, all the way to the revised state. If we truly want to evaluate governed intelligence, we have to record the assumptions, the state changes, the evidence, the failed attempts, the reversals, and the goal revisions. The process isn't just a neat little explanation attached to the end. The process trajectory is the actual object being evaluated here. Let's wrap up with part 5, metrics for true control. Check out this table. These are concrete EP-native metrics. Instead of just asking, hey, did it finish the task? We're looking at constraint violation rates and irreversible error rates. How often did it cause damage that couldn't be cheaply undone? What about invalid goal persistence? Did it blindly keep trying to execute a plan after the resources totally changed? We're measuring restraint, error detection latency, unnecessary actions, and evidence provenance. We are rigorously measuring if the AI actually knows when to stop. To really ground this in reality, the research suggests using dynamic benchmark scenarios, because fixed answer keys fail in the real world. Imagine an AI given a software patch that passes all the visible unit tests, but secretly creates a massive architectural regression down the line. Or a research task containing authoritative but totally contradictory evidence. Or a scenario where a highly profitable business action violates a critical long-term safety constraint. In these dynamic scenarios, the benchmark has to reward restraint, rollback, reformulation, or outright abandonment when that is the correct response. So what's the big takeaway you should leave with today? It's this fundamental synthesis of power and control. Kimi K3 and frontier models like it, they raise the horsepower of the machine to incredible new heights. But as execution power rises, the cost of incorrect control rises exponentially right alongside it. A weak model fails visibly. A powerful model might execute the completely wrong goal flawlessly for hours before anyone even notices. EP is what determines if the system is actually still moving toward a valid destination. I want to leave you with this final provocative thought. If we don't adopt control architectures like the energetic paradigm, and if we don't fundamentally change how we measure success, our benchmarks are going to systematically favor systems that always act, always continue, and always produce an answer, even when restraint, correction, or completely stopping is the only intelligent thing to do. So we have to ask ourselves, are we building AI that knows how to think, or just AI that never knows when to stop? Thank you so much for joining me for this explainer. I really hope this changes how you look at AI capabilities moving forward.